So first off, was really fascinating for me, an event, and I know that I'm the last thing standing between you and drinks, so I appreciate that you're still all here. So the somewhat provocative title of my presentation is kind of a selection of interesting puzzles that I have faced over the years. So I fell in love with predictive modeling more than 20 years ago, and I think it's because it was a way for the kind of eternal introvert of me to understand the world without having to talk to people. So you look at models and you're trying to figure out what they tell you about what's going on. And so often you find things that you really didn't expect. And sometimes that's great news and you learn something, and more often than not in data science, it's not great news because it might mean that you messed up somewhere. So I want to start with kind of the core of predictive modeling is that they try to find things to explain that help us forecast the future. And as an integral part of that, models tend to go wherever the signal is. And that's kind of a very almost obvious statement to make, but I call it the certainty vortex. Models really get sucked into this. So what do I mean by predictable? And so thinking a little bit about the space of problems, there are problems who are really, really, really hard. Not because it's hard to find the right representation, you can't figure out how to pick one model versus the other. It's just really hard to do a good job. So think, for instance, about what we know about the stock market. If you can get an accuracy of 55%, man, you're not here. You're rich somewhere on some island, right? So you know that this is not something that any model will ever do. It's not a matter of more data or the algorithm. It's just a hard problem. On the other spectrum, things like, is this a cat? Now, it might be hard to train a model to do it, and we have made huge strides recently, but any 3-year-old can answer this reasonably well. So these are, in principle, almost deterministic problems. Now, what my life has been devoted to is not cats or the stock market, but it's more about what do people do? Can we predict in medicine, in economy, like in different application areas, can we predict what people do? And the reality is, it really depends. So certain things that are easy to predict about people. For instance, that has been shown on Facebook data, it's pretty straightforward to predict your sexual orientation, given some amount of data about you. On the other hand, will I have pizza tonight? I have no idea. Honestly, I don't know what I'm going to do tonight. It depends who I run into on the way out. It's something that I can't predict it, let alone any model. So you have this scope here. What I really want to focus is what happens technically when you move from one end of the spectrum to the other. So let's try to predict who is male. And let's do that on a Facebook data set that was published where you have, for anonymized user IDs, a piece of information about the gender, as self-proclaimed, right? Look. In addition, you have a lot more information about what these people liked. And now let's build a model that predicts gender. Okay, try number 1. How well do you think I'm going to be able to predict the gender purely based on age? I shouldn't be able to, right? I mean, this seems like one of these things. It turns out you can, in fact, predict a little bit because there's some age correlation to people signing up for Facebook. But really, the accuracy is 60%, which is no surprise because there are 40% men on Facebook. But this is not the interesting part. What is interesting is a little bit of ranking. What is the distribution of prediction going to look like? So on a test set, let's assume I do everything right. No overfitting, no other messing up in the process. Let's assume I get it right. This is the distribution of the probabilities that the model predicts. Now, what's really fascinating about this is how kind of it's centered here. Ultimately, what do I want to do with this? I often need to find, for instance, recommendation systems or targeting systems, who is the top 10, top 1% of the population that I'm most certain about? Who's the most qualified candidate for you? What is the most relevant movie that you're going to show you, right? It's always about the highest predictions. Now, it turns out, despite the fact that the model is pretty awful by most standards, you're not that bad. You actually get 75% of that population right. They're men. Let's throw some big data at this. So I'm going to add in all the likes. So I'm just adding more columns, right? So this is same data set, more columns, more features. Accuracy is still not super impressive. What is interesting, though, is this is what the distribution of the probabilities that the model predicts look like. This model knows that it knows. It's very opinionated. And guess what? 100% correct out there. By the way, anybody wants to guess what's going on there? Why is the model so indecisive about the gender of this population? I love this. This is actually an audience of data scientists. Yes, they had no likes. Usually people kind of, well, maybe it's kind of a transgender, or people love to come up with stories for data. But yes, the reality is it's just kind of, you had no likes on those. Okay. What I want to show here is really how it progresses from very little information, and as you add more and more features to this model, it becomes more and more opinionated. That will be important in a moment. Because the reality is, the world doesn't come as either the stock market or the cat. A lot of applications that I see in my day-to-day life is a mixture. There's a little bit of stock market, and they're kind of cats all at the same time. Let me try to make this more. Okay. So here's a story. This happened in spring 2012. Over a period of 2 weeks, I work in advertising. Across hundreds of models, the average median lift doubled. These are all models that predict human behavior. And I hadn't done anything. So how can a system all of a sudden get so good? And it's not the death of free will. When we started to look and understand the model, what we found, these weird websites like Women's Health Space, and the model suggested that whoever goes to that website, Women's Health Space, is in the market for luxury cars, office software, credit cards, pizza, and hotels. In fact, there were a whole bunch of these websites that seemed very predictive, and none of them made any sense to me. So what do they have in common? Turns out what they had in common is the people who visited them. So we look at kind of an overlap of traffic, cookies that go to two websites at a very high overlap. And this is a graph of what that structure looks like. So every dot is a host name, and it's linked if there are more than 50% overlap. Now, let's take a look at what that means. So this is actually the Boston Herald, and this is all stuff about Boston. And so I can believe that there is like a 50% overlap. Now let's take a look at our friend right there. This is, in fact, where we see Women's Health Space, and a whole bunch of other stuff, none of which makes any sense. So what you're seeing here, there's no way that these are real people. What you found is a footprint of a bot network that is frauding the ad environment. And basically what happens is that these bots also go to brands' homepages, what's called cookie stuffing, because then the economic value of a cookie goes up. Now, what I mean here is what you're seeing in reality is not a single population, it's people and bots browsing the internet. And when I'm predicting who will go to the Chase homepage, I have both of them in there, and they both do it at some percentage. The problem becomes that people are hard to predict. We still have our free will and choices, whereas bots who were programmed to go to the Chase homepage are actually very easy to predict. Now, what does it mean for targeting? Well, if you think about this again in terms of the distribution of predictions, all of the probabilities that I get from my model for people are kind of in the middle. All the extreme probabilities that ultimately I will use for targeting will be bots, even if originally the bot percentage was really small. And so when we fixed that, our performance went back down, which for once was good news. Let's look at a few other models. And for instance, here's, can we predict who goes to a car dealership? Now, I have to come clean about the data I have. So I work in ad tech. By now, that should be obvious. And so we are constantly monitoring basically all of your digital devices. So we know an awful lot about you, too. It doesn't have to be the NSA. In particular, we may guess that you are at a car dealership based on the GPS signal that your phone sends me when it downloads an app for an ad shown in the free app that you're using while you're waiting for the guy to drive up your car. And then there's some kind of uncertainty about whether you're really there or just in the coffee across the street. There's also a bit of uncertainty whether this is really your home Wi-Fi, which I will use to connect the information to your browsing history. All this being said, let's throw it into a model where now we see three populations. The people who are actually at the dealership and their correct digital history. The people who are somewhere close by but not at the dealership, but I believe they are. And then there's whoever hacked into your Wi-Fi. So the person might be at the dealership, but the history doesn't belong to the person. So who goes to dealerships? It's actually really fascinating how good that model is, all things considered. These are the top-ranked logistic coefficients for the websites coming out, and you see a lot of in market signal. Then there is this story in marketing that people who buy a new house actually then buy a car, and apparently that's true. I see that. And let you come up to a conclusion why these people all of a sudden have the need to sign up for fitness. All this being said, the model works despite the fact there's a lot of uncertainty about the label on the different populations very well. Let's try this again. Where do we find frequent travelers? At airports. Okay, let me try to predict who will go to an airport. And here's my model. Okay, that's a little bit less obvious. Good. Number one, Spanish religious pages. Okay. Number two, that's interesting, attendance, jump seat news. Third group, football fans. And finally, and I will not comment on this, somebody who has a 3-day stay over in New York City and doesn't know what to do with himself, herself, themselves. What happened here? Is the model wrong? Well, I think it actually got it right. The problem is the frequent traveler has many other things to do with their lives, and they are much harder to predict than the people who actually work there. So the model certainly found people at the airport, just not the ones I hoped to find. My final example, now I'm moving on into the medical domain, was a data set from a data mining competition where we were given from Siemens Medical some fMRI data. And the task was, can you detect cancer in these images that they had converted into special regions, they call them candidate regions, that got then labeled. So this is the data that is given to me for 1,700 patients. And turns out we did really, really well. We won the competition, but also we did very great on any of their metrics that they were interested in. This is a version of an ROC curve, but a certain sliver. So very low false positive rate. We also were able to identify more than 60% of patients that we with near certainty could send home because we knew they didn't have cancer. Sounds great, like major breakthrough. Except when we started to look into this model, we found something odd. This is the distribution of the patient ID on the x-axis, and the y-axis is the prediction of the model. There is something weird going on here that should be pretty obvious once you actually look at this graph. There seem to be different ranges for the patient ID. It's much worse than that. This is now labeling people, candidate regions that had, in fact, cancer red and benign in green. And what this graph tells you is that the patient ID is by far the most predictive feature. Just tell me your number and I can tell you whether you have cancer. Now, truth be told, you shouldn't usually put the patient ID into a predictive model. This is not really good form. But there's a bigger understanding here. What the model had learned, with patient ID or not, is the location that this data was collected from. It's the grayscale, it's the calibration of the machine. And it only looked good in identifying cancer because it had backwards engineered the data generating process. It had understood absolutely nothing about predicting cancer. So in my last 13 seconds, what's the big picture here? I find it really fascinating. I think this is where your and our all skill comes in. There is an intuition about data science. You look at these things and they don't smell right. And this comes back to fail often. And in data science, the one thing you need to embrace is it's not failure, you learn something. If something even remotely doesn't smell right, it is our joint duty to figure out what's going on before we can leave these models out there to decide patients' fate. There is another message in here, and this is when you think again about this example of fraud and how it affects the prediction, and if you think about the fact that today the jobs you will be qualified for are decided by algorithms and so on, it's not even that models will reflect the biases of the data. Models create biases just fine by themselves, based on what they can predict and where they find the signal. And there are a number of examples where you really want to worry whether maybe your resume is a little bit too convoluted to make it easy to predict that you will succeed, despite the fact that your probability of succeeding is actually almost the same. It's just not something that the model can learn. It affects things like predictive policing. Maybe for some population it's easier to predict because there's more signal. It's not that this population is more likely to commit crime. It's just the model found something. And finally, a great study by Latanya Sweeney about biases when people get exposed in ad tech to, in this case, something like mugshots or other very unsavory offers and associations purely based on their name. I don't think this happens on purpose, but there is some secret lives to the models we built, and it's our duty to get to the bottom of it. Thank you.
What a great note to end the day on, this wonderful conclusion. We have time for just a couple of questions. This one, yeah?
So we have often infinite hypotheses that we could be asking, and I've heard data scientists argue that we should maybe just run a bunch of them and then pick the ones that turn out to have something significant, and they might, check that it doesn't overfit, but they kind of just use the computer instead of domain knowledge or theory. What are your thoughts on this? Do you think maybe we're missing maybe even potentially even bigger effects that we didn't think to ask about?
I think if nothing else, the presentation I gave really should speak to the fact that there is something else often going on that we didn't expect. I personally see there are certain domains like advertising where, yes, you can leave the machine to do what it wants, although the last example of Latanya Sweeney's work kind of questions even that. Having done predictive modeling for 20 years, I don't want the predictive model to make decisions that are important. I see this as a collaboration, as a second opinion. The way I envision using models in medicine is, yes, of course, there are small practices in locations that can't afford very high quality, educated healthcare. But having a system that has learned globally from all cancer is great. If the two of them agree, by all means go ahead. I think it's really interesting to use it as a second opinion where if there's a disagreement, it's our duty to find out whether the model was wrong for some of these reasons. So I'm looking for a collaboration. Machines shouldn't be taking over for a number of reasons I pointed out here, but we should work with them, together with them to take the benefits across all these different domains.
Sandra?
Hi again. Hi, Claudia. Thank you so much for an incredible speech, one of many today. I was curious to learn more about your reference to data science almost like a social responsibility, like we see it in journalism. Like it's our, I kind of felt like you were encouraging us to see ourselves as journalists, so reporting the truth through data science. So I was curious to learn more about that.
So it's an interesting analogy that I hadn't really thought about, but I think quality control is one of the hardest parts of data science. I myself can't tell you whether if I spend another 2 weeks on this problem, the performance of my model will go up by 1% or 15%. And if you come to me and say, hey, I built this model and here's its performance, I have to take your word for it, because other than me going back and redoing everything, which was almost kind of the example of the statistics here, it's really hard to verify how good this is. And that means it really becomes our moral duty when we build these things to do absolutely everything in our powers, from understanding all the way at the beginning how the data was created, to of course doing all of the out of sample. I'm not even talking about this. This is kind of table stakes. But I feel there has to be a personal responsibility because you cannot delegate it. With journalism, at least I can send 3 other people to investigate and maybe they will tell me there's something fishy. With my model, any of them, there's no way any of you can figure out there was something fishy because the degree of complexity that goes into that model, there was this great example of the talk we had earlier, it's really impossible to recreate that. And that's how I feel. It has become my responsibility. In the old days, I just built really, really good models. These days, I'm always scared when the model gets too good. There's usually something wrong.
Write that down, okay? Write that down, everybody. We are going to finish today with a question from Twitter, which I think is very appropriate. So,
how long does it take you to discover the stories behind the weird results you've gotten?
You know, the worst is, I'd say I found 50% of the weird stories in my models in my life. So I think there's a dark pool of stuff I just haven't spent enough time yet on finding this out. And often this is purely accidental. How did I find the breast cancer case? Yeah, I didn't put the patient ID into the model, but at some point I sorted the data and I had it running over my bash on the screen. It's kind of, this is supposed to be a 6% base rate and every third one of them is positive. This is how I found it. So it's almost accidental. Some of the bigger ones in the advertising, usually it takes me a day because the process is so familiar. I've been building these models for so long. But if you build the process of modeling for the first time, you probably spend more time finding the problems than just hacking it together the first time around. So just plan on spending a lot of quality time with your data.
Yeah. Well, we're all looking forward to that. And thanks so much again, Claudia. Fantastic talk.